Welcome to our journey into the world of electromagnetic waves. Have you ever wondered how radio waves, microwaves, or even light waves travel through space? How can these waves be used to transmit information across long distances? The answer lies in the Maxwell's equations, which provide a complete mathematical description of the electromagnetic phenomena. Depending on the medium properties and the distribution of electric and magnetic sources, we get different solutions to Maxwell's equations. In this video, we'll investigate the solution of Maxwell's equations in an unbound source-free medium for time-varying fields. Assuming that the time-varying electric and magnetic fields exist in an infinitely large medium, we'll explore the fascinating world of uniform plane waves and their importance in understanding the electromagnetic wave propagation. We'll start by breaking down the basics of what plane waves are and how they work. Then we'll dive into the concept of uniform plane waves, which are waves in which the electric and magnetic fields are in a plane perpendicular to the direction of propagation, and the magnitudes of the fields are constant in that plane. We'll discuss the properties of uniform plane waves and their applications in various fields, including communication systems, waveguides, and antennas. For the case of Maxwell's equations in an unbound homogeneous medium for time-varying fields, the simplest solution is the uniform plane wave solution. This solution is an important fundamental phenomenon of electromagnetics as it provides the basic understanding of electromagnetic wave propagation. Although we don't have unbound or ideal homogeneous media in practice, the concept of uniform plane wave is still very useful, especially for media that have physical dimensions much larger than a wavelength. By the end of this video, you'll have a better understanding of how electromagnetic waves propagate and how they can be used in various applications. You'll also have a deeper appreciation for the fundamental importance of uniform plane waves in understanding electromagnetic wave propagation. This video includes 3D animation scenes that depict the concept we're discussing. Alongside the 3D graph, we'll also show you the top view, side view, front view, or a combination of all three views to help you better understand the topic at hand. By presenting the concept from various perspectives, you'll be able to visualize how it works and gain a deeper insight into its behavior. So sit back, relax, and let's dive into the fascinating world of electromagnetic waves and uniform plane waves. Suppose we have electric field oriented in the x direction and having a magnitude represented by the length of the vector. The magnitude, or the length of the vector, is changing only as the vector moves in the z direction. A sinusoidally varying electric field, and the variation is a function of distance along the z-axis. If the vector moves in the x direction, there is no change in the magnitude. Also, there is no magnitude variation when the vector moves in the y direction. In other words, the vector is uniform throughout the xy plane. The magnitude is a function of z only. This can be represented mathematically in this form: a vector oriented in the x direction, and its magnitude is a sinusoidal function of z. This is called a uniform plane electric field. The electric field at each point in the xy plane is the same magnitude, and the same orientation. As we move along the z-axis, The magnitude of the field at each point in the xy plane is changing the same way. A sinusoidal variation is a function of z. Although they are varying as a function of z, the vectors are the same throughout the xy plane. So at each point in z, we have a different uniform electric field. Besides being a function of distance, electric field can also be a function of time, and the uniform electric field is no different. Here's a uniform plane electric field changing sinusoidally with respect to time as well as distance along z, meaning at each instant of time, for instance at t equals 0, as the z change, the electric field varies sinusoidally. Here we are freezing the time and just sweeping the distance along z. At t equals 1, same thing happens. The vectors are changing sinusoidally as we sweep z. Same thing applies at each value of time. Also at each value of distance, for instance at z equals 2, the electric field is varying sinusoidally as we change time. The electric field is changing sinusoidally with respect to time at each value of z. Magnetic field can also be uniform plane, just like the electric field. So uniform plane electric or magnetic field is uniform throughout a plane. It can be varying as a function of distance of a direction perpendicular to the plane. It can also be a function of time, or both time and distance. Maxwell's equations are a set of 4 fundamental equations that describe the behavior of electric and magnetic fields and their interactions with charges and currents. They are also used to derive the wave equation for electromagnetic waves, which describes how these waves propagate through space. Gauss's law for electric field states that the total electric flux through any closed surface, or the divergence of electric field, is proportional to the total electric charge enclosed within that surface. Gauss's law for magnetic fields: the divergence of magnetic field, or the magnetic flux through any closed surface, is always zero. There are no magnetic charges. Magnetic field lines always close in themselves. Faraday's law states that the curl, or the space derivative of electric field, is proportional to the time derivative of magnetic field. When a magnetic field changes over time, it induces an electric field that rotates in a plane perpendicular to the direction of the magnetic field. In other words, a time-varying magnetic field generates a rotating electric field. or a space-varying electric field. This relationship is known as Faraday's law. Here we have a sinusoidally time-varying magnetic field. That magnetic field generates a sinusoidally space-varying or sinusoidally rotating electric field. So the next time you see a magnetic field, remember that it's not just a force, it's also a source of electric field. Ampere's law with Maxwell's modification states that the curl, or the space derivative of magnetic field, is proportional to the electric current density plus the time derivative of electric field. When a wire carries an electric current, it creates a magnetic field that rotates on a plane perpendicular to the direction of the current. Similarly, a time-varying electric field produces a rotating magnetic field in a plane perpendicular to the electric field. This relationship is known as Ampere's law with Maxwell's modification. We now understand that both electric current and time-varying electric fields can generate rotating magnetic fields, expanding our understanding of the complex interplay between electricity and magnetism. I have a separate video for Maxwell's equations. You can watch it for more details. Now suppose we have an unbound medium. It can be free space, it can be something else, and that medium is free from any electric charge or electric current. The electric and magnetic field in that medium, as well as their interactions with each other, are described by the four Maxwell equations. Since there is no electric charge or electric current, then the Maxwell equations are reduced to that form. First two equations are equal to zero, meaning there is no static electric or magnetic field in that medium. Now suppose we have kind of uniform plane electric field in that medium. That field is uniform in the xy plane and varies sinusoidally as a function of time and z. The first two equations are equal to zero, so the only source of that electric field is a magnetic field, as you can see from the third and the fourth equations. The space derivative of that magnetic field is equal to the partial time derivative of the electric field, and the space derivative of the electric field is equal to the partial time derivative of the magnetic field. So from Maxwell equations, for that electric field to exist in that medium, a magnetic field must exist so that the curl of it generate that electric field, and the curl of the electric field generate the magnetic field. For the Maxwell equations to be valid in that medium, electric and magnetic fields must coexist. Substituting the electric field into the third formula to get the corresponding magnetic field and doing some math with the fourth equation, you can find out that the corresponding magnetic field is also uniform plane and having that formula. It's a uniform plane as the corresponding electric field, oriented in a y direction and varies sinusoidally with respect to time and z. Now let's make it easy and look at just a single point in the xy plane and see how the electric and magnetic field in that point are changing as a function of time and z. The electric and magnetic fields in that point are lying in the xy plane and perpendicular to each other. If we freeze the time and varying z, for instance at t equals 0, as z changes, the magnitude or the strength of the electric and magnetic fields is changing sinusoidally with it. And that is clear from the formulas. The electric and magnetic fields are oriented in the x and y direction respectively and varying sinusoidally as a function of z. Not only that, if we fix them at a specific value of z, then as time changes, the magnitude of the electric and magnetic fields is changing sinusoidally with time. That happens at each value of z. Now let's look at the whole xy plane. At each value of z, the electric and magnetic fields are changing sinusoidally with respect to time, but they are uniform throughout the plane. Each point in the xy plane is having the same field strength, and the fields are changing sinusoidally throughout the plane. At each instant of time, for instance at t equals 5, the electric and magnetic fields throughout the plane are changing sinusoidally as a function of z. Let's look at the single point in the xy plane once again. At each value of z, from the formula, the point is having electric and magnetic fields with a specific strength given by the sinusoidal relationship. As time goes on, the fields at each value of z vary sinusoidally with respect to time. As you can see, it feels like the fields are moving in the positive z direction as time goes on. At every point along the z-axis, there are two vectors that represent the electric and magnetic fields. These vectors have magnitudes that vary sinusoidally with time, even though their positions remain fixed. As time progresses, the overall wave moves along the z-axis, despite the fixed positions of the vectors. This is because the magnitudes of the vectors are functions of both time and distance along z. Therefore, the electric and magnetic fields at any given point in the z-axis change over time, creating a dynamic wave that propagates through space. This is the most simple case of electromagnetic wave propagation, the uniform plane electromagnetic wave. The electric and magnetic fields are perpendicular to each other, and both are in a plane perpendicular to the direction of propagation. By looking at the whole xy plane, you can see how the plane wave is uniform in the xy plane and propagating in the z direction. A plane wave is a type of electromagnetic wave that exhibits uniform electric and magnetic fields throughout the xy plane at each value of z. The electric field has the same magnitude and orientation throughout the plane, while the magnetic field is perpendicular to the electric field and also has the same magnitude throughout the plane. The fields within each plane change sinusoidally with respect to time, resulting in a wave that appears to propagate along the axis as time passes. It's fascinating to consider the elegant, fluid motion of these waves as they traverse through space, and the intricate interplay between their electric and magnetic components. Each point in the xy plane has electric and magnetic fields oriented perpendicular to each other, and vary sinusoidally with respect to time and z. So this graph is nothing but this graph repeated throughout the xy plane, taking all the points into consideration, not just a single point. In other words, this graph you're looking at is a repetition of itself throughout the xy plane, encompassing all points in its domain rather than just a single point. Now, since the electric and magnetic fields are uniform plane, each has the same magnitude and the same orientation throughout the xy plane. Instead of using vector fields, we can represent each plane with a single color representing the magnitude of the electric and magnetic fields in that plane. At each value of z, for instance at z equals 5, there's an xy plane having a color representing the magnitude of the electric and magnetic fields within it. As time goes on, the magnitude of the fields changes sinusoidally, hence the color changes sinusoidally. Here's the whole picture in 3D. Since the fields are uniform throughout the plane, we assign each plane with color representing the magnitude of the fields. Since the fields are changing sinusoidally with respect to time and z, the colors are moving along z as time goes on. This is the plane wave propagation in free space. Now we saw how electric and magnetic fields are propagating in an unbound medium in its simplest case, the uniform plane wave. Electric field is volts per meter, while the magnetic field is amperes per meter. This kind of propagation is very similar to how the voltage and current waves are propagating in transmission line. I have a series of videos explaining transmission lines in more details. Seems like we can transfer electric power in an unbound medium, just like we do in transmission lines. Now the ratio of electric field over magnetic field is a quantity has units of ohms, volts per meter over amps per meter. It represents the characteristic impedance of the medium. So to have a wave propagation, which means electrical energy transfer in an unbound medium, electric and magnetic fields must coexist. Not only that, they obey Ohm's law, such that the magnetic field is equal to the electric field divided by the characteristic impedance of the medium. This is exactly analogous to the fact that the current flowing through an impedance is equal to the voltage across it divided by the impedance value. As the impedance value change, the current flowing through it change for the same voltage. Same thing here. Each medium has its own characteristic impedance determined by the permeability and permittivity, and based on the characteristic impedance, the electric and magnetic fields constructing the uniform plane wave are related based on the Ohm's law. For free space, the characteristic impedance is approximately 377 ohms. So in free space, the magnetic field is equal to the electric field divided by 377 ohms and oriented in the same plane and perpendicular to the electric field. And just like in AC circuits, the average power flow of electromagnetic wave is equal to the real part of the cross product of electric field and the complex conjugate of the magnetic field. Cross product means that the average power is a vector perpendicular to the plane containing electric and magnetic fields. There is complex conjugate here because the electric and magnetic fields are expressed in form of complex exponential functions. We just took the real part of it, which is cosine. The average power consumed in AC circuits is the same as this formula, with voltage and current replacing electric and magnetic fields. So any unbound medium such as free space can transfer electric power from one point to another in the form of electric and magnetic fields, or electromagnetic waves. and the free space can be modeled as a 377 ohms resistor. That's a very important concept that we will revisit when we talk about antenna. So in electric circuits, power can be transmitted from one point to another in the form of voltage and current, which are related by Ohm's law. In free space or any insulating medium, on the other hand, power can also be transmitted from one point to another, but in the form of electric and magnetic fields, which are analogous to the voltage and current and also related by Ohm's law. So far, we have assumed that the medium is unbound, and there is nothing interrupting the wave. While propagating, if the wave is interrupted by a reflecting surface or entered another unbound medium with different permeability and permittivity, then based on the surface or the medium, part of the wave is dissipated in the surface and the other part is reflected back. This is modeled by a backward traveling wave. So the electric and magnetic field of electromagnetic wave propagating in any unbound medium is consisting of forward traveling wave representing the forward motion and a backward traveling wave representing the reflected wave. This formula is exactly the same of how the voltage and current waves propagate in transmission lines. I have a separate video explaining that formula in much more details with 3D animations. I've also explained the process of reflection and transmission lines, which is similar to the reflection of waves in unbound medium. This formula is the solution of the wave equation, which is derived from Maxwell's equations. You can revisit the transmission lines and Maxwell's equations videos to see the derivation. Now our assumption was that the electric field varies sinusoidally with respect to both time and z. But the variation doesn't necessarily have to be sinusoidal. It can take any form. According to Fourier analysis, any signal can be decomposed into linear combination of sinusoids. Having the ability to analyze the behavior of a wave under sinusoidal variation enables us to analyze the wave under any other type of variation by decomposing it into a sum of sinusoidal functions.